Okay, this is part 5. This will be the final video of the respiratory system for chapter 23. I'm Jamie Batts, I'm your instructor, and let's see. We ended up talking about, in the last section, how the pons and medulla oblongata control respiration. The chemoreceptors are, again, as I mentioned, they're sensitive to the partial pressure of carbon dioxide and pH. So, and those two things are linked anyways, but you'll see that. They are located in, again, the aortic bodies, the carotid bodies, and those chemosensitive areas of the pons and the medulla oblongata. And so those different areas all kind of have feedback loops together. Let's talk about, let me give you another couple scenarios so you understand how respiration works and some of the feedback loops. I do want to point out page 842 shows you all the nitty-gritty for what is happening in the red blood cells. I did not mention the chloride shift when I was talking about the bicarbonate, just because I was trying to simplify it. That chloride shift is important to understand. It's just an exchange of bicarbonate for chloride, and then it switches again. And you see that diagrammed out on page 842. And again, we'll revisit the bicarbonate buffer system back in chapter 27, I think it is. So if you don't quite get it now, that's okay. Understand the big picture, understand why this happens to carbon dioxide and kind of the fates of carbon dioxide in the blood, but you don't have to get caught up in all the little details just yet. It's coming. So let's talk about some scenarios. What is happening, erase my board, what's happening if you have an increase in carbon dioxide. Maybe something's going on in the cerebral spinal fluid, or maybe the flow of blood is cut off from the brain for some reason. So you have an increase of carbon dioxide, partial pressure carbon dioxide, PCO2, in one particular area. Sorry. And basically that's caused by a decreased pH of the CSF, cerebral spinal fluid. pH is decreasing, which means it's getting more acidic, right? So what are some things that are going to happen if this occurs? Well, first of all, it's going to lead to rapid breathing. This is your body trying to bring in more oxygen, trying to get rid of that carbon dioxide. And so the alveolar concentration of CO2 is going to decrease, right? That's the concentration of carbon dioxide decreases. Alveolar concentration of carbon dioxide decreases. So what happens then? Well, then you're going to have an increase in diffusion of carbon dioxide out of the body. It's kind of a good thing, right? Or, right, this is one scenario. Or you could continue with your rapid breathing, like hyperventilating. Hyperventilating can, if this stuff doesn't occur afterwards, hyperventilating could lead to a decreased partial pressure of carbon dioxide, which is called hypocapnia. Not having enough carbon dioxide, which seems kind of ironic, right? I mean, you want to get rid of carbon dioxide, don't you? Carbon dioxide is a waste product, but again, not really. You need it in balance, in ratio. You need it in equilibrium with everything else that's going on. So if this is happening, your respiration rate is going to continue to increase. Your respiration rate is going to continue to increase. And eventually you can get back to homeostasis just by controlling that respiration rate and not letting it go out of control. Again, in hyperventilating, this would be if I would say, okay everyone, let's take 20 quick breaths right now. right? What happens if you don't actually do it? Because what is going to happen is you're going to get lightheaded. And that lightheaded is this hypocapnia that's taking place, making you a little dizzy and setting off your chemoreceptors, setting off your respiration rate. And then what it's going to do is it's going to slow your respiration rate down if you're not consciously controlling it anymore. Once your body takes over, it will calm it down and get you back to normal. So let me check your book and make sure that I'm covering everything that's in it, because I think we're pretty much done here. The major regulatory mechanisms. I didn't mention the Herring-Brauer reflex, but that's the stretch reflex. It's basically saying that your lungs can't overinflate themselves. Makes sense, right? They're not going to keep inhaling until you blow up like a blueberry, right? You're gonna stop. You have your nice little homeostasis chart there on 846, a little diagram, kind of like what I just described for you, and some adjustments when you exercise and as we age, and then the diseases and disorders that affect asthma, as well as emphysema, etc. So all little snippets and little pieces of the respiratory puzzle, if you will. Please let me know if you have any questions, and I hope you guys have a great week. I'll talk to you later. Bye.